Greetings to all. Today we will learn about the building which is standing tall right in front of your eyes. It got various names with time. At first it was called swissretower. Then people started calling it with the nickname the Gherkin because it resembled the shape of a cucumber. And officially it is known as 30 St. Mary X. It wasn't built for no reason. Let's see its history to know why was it built at the first place. The former buildings on the site, including the home of the Baltic Exchange, had been severely damaged by a terrorist bomb attack in 1992. So, the previous buildings on the same site were destroyed. The location and history of the site demanded a design of the highest design quality that would make a real contribution to the urban environment of the city. Officials decided to put a larger tower at its place. First idea of Millennium Tower failed due to the fear of negative effect on air traffic and more. Architect Norman Foster came up with scaled-down design which is now known as 30 St. Mary X. Look at this view. Isn't it astonishing? Let's see what is its purpose. The Gherkin is a modern commercial skyscraper located in the primary financial district of the City of London. Construction started in 2001 and was finished in 2013. It wasn't up till April 2004 that the building officially opened. As well as looking pretty sweet, the swirling striped pattern visible on the exterior has a structural point to it too, the result of the building's energy saving system, which allows air to flow up through the spiraling wells. There are 18 passenger lifts in the building. 378 people can be vertically transported through the building at speed up to 6 meters per second at any time. This is overall information of the building. It is located in London, United Kingdom. Floor area is 47,950 square meters. It has 41 floors. And these are the architect, structure engineer and the contractors of the building. This is how it looks from far away. Its height to the top of the dome is 179.8 meter, which is almost 180 meter tall. In plan, this is its top view. Largest floor external diameter at level 17 is 56.15 meter. The largest circumference of the Gherkin is only 2 meters less than that the building's height. Well, not quite, but the circumference at the Gherkin's widest point is 178 meters, which is only 2 meters less than its height, which is 180 meters. The building's footprint at bottom is only 50 meters in diameter and the site area is also quite large, 0.57 hectares. Same as any commercial building, the office floor to floor height is 4.15 meter. Now let's go into technicality of the building. It is majorly a steel structure. The total weight is divided into few parts. Let's see, but what is the total weight of the steel which is being used in the building already? It is 8358 tons. Oh my god. So 29% of the steel is used for the Diagrid. We'll see what Diagrid is. 24% is used for the core columns and 47% is used for beams. Starting from the very bottom, the most important part of structure, that is foundation. Looking at the building, can you guess what type of foundation it is? Pile foundation. 750 mm diameter straight shafted piles into the London clay. Number of piles? 333. Total length of piles is about 9 km and the design capacity of there is 117,000 tons. But why pile foundation? Pile foundation is mostly used because firstly, it resists heavy load. Being a tall building, the incoming load of the structure is very large. Also, these are inserted into the London clay. The structure is built on a clay soil, hence the bearing capacity of the soil is very less. An irregular plan of structure. As the radius of the building varies with height, the load distribution is not uniform. Therefore, pile foundation is used to prevent the differential settlement. Interesting fact. It is known that due to some site restrictions and in order to create a monolithic foundation, all the piles were inserted in one single day. Did you see the shape of this building? Not just for good architectural look, but there's a science behind it. It is aerodynamically designed. One of the critical factors while designing the tall structure is nothing but wind load. The tower is aerodynamically designed to reduce the wind load on the structure. Let's divide it into three parts: bottom, middle and top. The lower part tapers so that wind wraps around the tower. The aerodynamic shape at the mid directs the wind around the building, improving pedestrian comfort at street level and reducing lateral loads on the structure. At the top, the tapering at the crown allows sunlight to reach down to the plaza. Such a mindful thought for each and every part of the building. What else does this shape influence? The striking of wind on the structure decreases. Decrease in vibrations of the structure occurring due to the wind. The slight irregular movements caused by wind diminishes. Yeah, something interesting has taken place. Each floor is rotated by 5 degrees. But why? This twist creates balconies at each level and opens up dramatic views through and out of the building. Wow! Two important structural elements of the formation of this building are: first, primary structure, which is the external one, known as Diagrid. It is helpful in resisting horizontal and gravity loads. We'll see what is Diagrid, do not worry. And secondary structure, the internal one, is the core. It resists vertical gravity loads, provides rigidity, resists torsion, increases stiffness. We'll see this in deep too. Here comes the one. Heard about Diagrid for the first time? Let's see what it is. Diagrid word is composed of diagonal plus grid. Diagrid is an external structural system in which all vertical perimeter columns are eliminated. So it's a building without any columns and consists of only inclined columns on the facade of the building. Shear and overturning moment developed are resisted by axial action by these diagonals as compared to the bending of vertical columns in frame tube structure. Why is it used here? The digrade responds to the building's curved shape and provides vertical support to the floors, thus allowing large internal column-free space for the office. In addition to being highly efficient in resisting wind forces, the digrade frames the communal light wells which spiral up to the building, enabling occupants to enjoy natural light over a larger area of floor. You must be wondering what are light wells. We'll see that too. A balanced digrade structure is formed by generating a pattern of columns spiraling in both directions, intersecting at two stereo intervals at node points. Node points is another interesting topic we are going to look to. This gives rise to significant horizontal forces at these points, even under balanced gravity loading. This is how there are no columns in the structure and still it stands still. Now, how is it used? Well, this is going to be a very long journey, but keep up with me because it is going to get interesting. The variation in the digrade geometry results in compression in the hoops. Hoops are the circular perimeters of the building. Compression in the hoops at the top of the building where the columns are more steeply angled and lighter loaded, and very significant tension forces at the middle and lower levels. The horizontal hoops turn the digrade into a very stiff triangulated shell, providing excellent stability for the tower and equilibrium for any asymmetric or horizontal loading conditions. This means that the core is not needed to resist wind forces and can be designed as an open, planned, still structure, providing adaptable internal space. Foundation loads are also reduced as a result. The sizing of the steel elements is governed by strength criteria. The total sway stiffness of the digrade is sufficient to limit the wind sway to 50 mm over the full 180 meter height and provides a very good level of overall dynamic performance. Isn't this digrade just a fantastic solution to many problems? So, we came across digrade nodes. What are these digrade nodes? At the intersection of the diagonal elements, the junction requires connection of these elements, which are done with the help of nodes. These nodes are composed of welded steel plates to which the diagonal elements are joined. Nodes are capable of transferring loads vertically as well as horizontally. Hence, success of a digrade structure mainly depends on its connection details. So how was the development of the digrade nodes prepared for this particular building? So this is an drawing. Let's see in depth. The local geometry of the connection varies at each floor. My God, there are 41 floors and the geometry varies at each floor. That is a lot of work. Due to the differing floor diameters, the triangulated nature of the digrade demanded a detailed consideration of the total control of fabrication and erection tolerances. Two design approaches were possible. One can focus on the individual elements and fabricate end details to suit each situation, or use separate node pieces accommodating all the geometry variation and allowing simple stick elements to be used. We have seen the node pictures in the previous slide. The later approach allowed a simplification in the connection geometry to the consideration of 3 intersecting planes relevant to a node, as opposed to 6 individual element orientations. One plane is defined by the axis of the horizontal hoops. One is common to upper columns and one to the lower columns. Principal compression loads are transmitted to milled end bearing surfaces and tension through bolted splices. The significance of the Diagrid connection detail to the steelwork contractor's method of working in both shop and site made it important for all potential contractors to be given the opportunity to develop their own ideas and approach. Now, the second most important part of the building is its core. The central core resists the vertical load and is free from any diagonal bracing. The internal structure of the building comprises conventional steel beams and columns with composite profiled taking floors. Main functions of core are: it resists vertical gravity loads, provides rigidity, resists torsion, and increases stiffness. But how does it do it? The core is the primary system for transferring vertical gravity loads to the foundation. It is a rigid frame made up of movement-connected steel members. The core also ensures that the horizontal hoop system does not splay outward by acting as a tie back from the Diagrid. The core's central symmetrical placement within the building does not allow torsion as an effect from lateral loading. High structural stiffness is advantageous when dealing with loose soil types. Yes, I told you we will see what are light wells. Heard about light well? Somewhere, as the name suggests, it may be associated to something that provides light. Let's see what exactly it is. Flexible and adaptable office space demands a regular interval spanning grid. The office floors at 30 centimeters X are organized into 6 spokes or fingers, arranged on a 1.5 meter grid around a circular surface and lift core. Between the spokes are triangular zones that are used as perimeter light wells. The result is a maximum 14 meter core to glass internal dimension with all parts of the office fingers within 8.5 meter of a light well. The light wells are offset at each successive floor by 5 degrees. Thus, twist creates balconies at each level, as we have seen before, and opens up dramatic views through and out of the building. As light travels, these wells or shafts and naturally lights the 6 radial zones of the buildings. Therefore, it is known as a light well. Not only does it provide light, but also helps in natural ventilation and circulation of the building. Now let's see how is the floor framing done for this particular building. The circular floor plates are framed between the core and the perimeter structure using radial beams on 10-degree center lines. So the rectangular type of grey portions that you can see are nothing but the floors. The overall slab thickness is 160 mm with a similar weight to more conventional 130 mm and also provides improvised overall floor plate vibration dynamics due to the increased rib stiffness. Beam depths are minimized by use of wide flanged European profile beams. The beam depth is most critical part in the primary services distribution zone around the core, whilst there is a less critical fit at midspan. This enables the beam to be specified without precamber. What is a precamber? having a camber design in such a way as to reduce deflection under load, whilst maintaining adequate clearances for service. Within the cores, the beam spans are much reduced, allowing the horizontal separation of structural and services zone. The only area where beam web penetrations are required is around the perimeter, where supply and exhaust air is ducted via plenum boxes. What is it? In building construction, plenum is a separate place provided for air circulation for heating, ventilation, air conditioning. It is commonly found in the space between the structure's ceiling and a drop-down ceiling or under a raised floor. Now, imagine being at the top of the building at its dome. The upper three levels of the building, from level 38, provide corporate facilities for Swissre and other tenants 360-degree views over London. These levels are enclosed with a steel and glass dome structure of 30 meter, rising 22 meter from its support on the top of the perimeter Diagrid. The dome steelwork is a fully welded lattice of intersecting fabricated triangular profiles. The efficiency of this structural arrangement results in very minimal steel elements that are only 110 mm into 150 mm large. Now, the glazing glass, that is facade, it works as windows, building cover, weather resistant, helps in energy consumption and whatnot. Facade is a bundle of benefits. For this structure, it is cladded with double paned glass which is filled with argon. The glazing to the office areas consists of a double glazed outer and single glazed inner screen. Sandwiched in between is the ventilated cavity which reduces heating and cooling requirements. The solar blinds intercept solar gain before it enters the office environment. Last but not the least, let's go through the construction stages. The erection sequence progressed in two-story bands in the following pattern. First, the core steel was completely erected with access stairs and few temporary bracings. Then the deck was placed and the survey points were established. Diagonal columns and nodes were erected. Radial beams, plumb, hoop members were erected. Then the flooring frame and decking was done. Then the floor was concreted. Thank you so much for watching. Please like if you find this useful. Comment what else you would like to see and which structures. Also share if you find any crazy engineer or enthusiast, and stay tuned by subscribing.